So in terms of OCRA, I'm going to be covering Edexcel, but A-level maths is really universal. So you could probably relate most of the stuff that you get from here. If there's any specific thing to do with OCRA that is slightly different, do let me know. But if you compare the different exam boards, they practically do the same sort of thing. I think certain exam um, styles are slightly better, slightly different, and they'll sort of dance around certain exam questions. So if there's any specific exam questions that you guys want to go through from your specific exam board, happy to just say that in the chat, and then I can quickly Google it and we can go through the question. Oh,
Aska, please just make sure whenever you're doing it that you keep checking the waiting room, as I think lots of people were
yes.
in the waiting room for a while.
I
I'll
see,
let
I
you
see.
take over host again. I've just let them all in.
Thank you. I saw the participants number and then I didn't see that I should have let them all in.
No worries.
Thank you very much. Cheers, Jess. Hi everyone. Apologies. I forgot to let people in. But as I've just mentioned to the first few people, can you guys let me know specific topics that you guys would want to cover? So I have got integration, stats, trigonometry, differentiation, range and domain, mechanics. That's an interesting one. Um, and so then we'll sort of quickly talk through sort of certain types of how you would how you would revise maths. Proofs are interesting. Parametrics, trig identities. Yeah. Complex components. Okay, so it's going to be mechanics. Yep. Trig integration. Yeah, there's a lot of stuff. 3D vectors. Okay. Binomial expansion. Yeah, okay. Complex components, forces stuff is what I meant by met. Okay, forgot it. That's fine. Moments. Moments is okay. Um, well, it's sort of year 13, but also year 12 as well. Year 12, you can do it fairly quickly. Projectiles is also interesting. No, this does not include further maths. But the skills you learn from the differentiation and integration here will include further maths. I will add a little thing about further maths too. If you need to do further maths, I would recommend just going through the book. And then after that, you can sort of go through um, just exam questions. And I would recommend looking at Mad Ass Maths too. That's what I used for my further maths content. Okay, great. So there seems to be quite a few contacts indeed. Sequences and series. Okay, right. Okay. Any other topics? Please do listen out for the specific iteration. Oh, interesting. Okay. I'm gonna basically just go through a few things. Yeah, I mean, it ends up, I think it seems like we're basically going to try to do the entire spec in about an hour. So let's see what we can do. Right. Stats normal, normal stuff. Okay. So this is the list of topics. Um, And so the first year one stuff is relatively pretty fine. And the thing that kind of gets people is probably circles. I know circles some people find difficulty with. Um, and also with your ideas of algebraic methods. I know that some students are struggle with range and domain. All you need to remember for that is that domain is what you put in and the range is what you get out, right? Range, think about it as like throwing a ball, right? Because that's kind of like the range of what you get, like the result of it. So think about what you get out and then what you get in. And everything about that is just about thinking about how the function works. And I would always draws, like draw the function, sketch the function, you will be fine afterwards. You'll be able to see where are my asymptotes? Where are the regions where I just can't access it? Where are my zeros? Find where you're dividing by zero. That is most definitely um, a asymptote, right? In terms of integration and differentiation, remember the specific types. So one of you guys asked me just earlier, how do I revise all the derivations. Be very familiar about what derivatives and what integrations are in your formula booklet. This might be a weekly class. I think we're gonna run another one at some point. But remember what is in the formula booklet, because from there you can actually jump off of points if you know certain tricks, right? So if you know in the formula booklet, you will have the integral of this function is this, which means that you actually know what the derivative of that, because you can just go backwards, right? And that kind of like quick thinking will help you so quickly. And a lot of students don't really look at the formula booklet. And then for differentiation and integration, think about um, the specific rules that you have, right? So for differentiation, um, you only have three, right? For differentiation, you kind of only have the three main ones, which is product rule, quotient rule, and chain rule. And so when you're spotting a new exam question, you want to think, okay, have I got two functions that multiply together? That's a product rule. Have I got a function where it is f of x over g of x? Then that's the quotient rule. Or is it the chain rule where I have a function of a function? And you can have, three functions that could be like f of g of x multiplied by h of x, right? And these are probably two different functions. You could have something like cos of x squared multiplied by 2x. If you're differentiating this, take it in steps, right? Take it in the larger step. You're differentiating these two, so you want to split those up with product rule, and then you do quotient, so chain rule in the inside. So that's how I think you should look at differentiation. And then beyond that, if you understand these three frameworks, you look at your formula booklet to sort of like make sure that you've got everything. Okay, I'm gonna just yeah, just make sure everyone's in. Just let's do. Okay. So does that make sense for the differentiation? There are some interesting questions that we can go through. Nice. For integration, again, there's only a few, there's actually less things to think about with integration. But think about just the backwards of differentiation. So if you know how to differentiate this one thing and you change it by a specific constant, you know how to integrate it. But with integration, again, there are the specific um, that's a very good point. So we'll go through some exam questions. And with integration, you want to think about just the two things, right? So that's going to be reverse chain rule. So in theory, reverse chain rule is just that if I have two functions, like f of x multiplied by g of x, is there one that is easier to integrate and one that is easier to differentiate, right? So that's why we're integrating, v du, which is equal to uv minus the integral of, so that should be u dv, integral of v du. And you realize that this is actually just the opposite of the chain rule. This is actually what the reverse chain rule comes from. Because if you take chain rule, which is you have two functions, you take the derivative of this, it's going to be u dv plus v du, right? We're taking, this is f of x, g of x, f of x different derivative of g, and g of x derivative of f, right? And you just split this apart, or you can take the integral of both. Um, so like this, right? I take the integral of everything. I look at this. UV equals, or if I take the integral of the derivative, that becomes nothing, right? As the integral of u dv plus the integral of v du, which if you rearrange, you get the top. Yes, good. You can integrate those parts twice because you can see something that looks like maybe this, x squared cos of x, right? Where you can see that this is going to be way easier to differentiate. And so you would differentiate this and you would integrate this. Because then at some point, you're going to end up with cos x, some trig function is probably going to be x sine of x. You differentiate again, or you integrate again because you want to differentiate that x squared get to leave yourself with just a cos x, and you're probably going to get something like plus or minus somewhere here. And so you can see that this thought process of integrating by parts is to just remove that x squared x1 so that you remove this thing. The problem with integration that's difficult is that if you're multiplying two functions together and you're integrating it, that's hard to do. Oh yeah, of course. So if you're integrating, you know, something that is a multiple of two functions, that's quite difficult. And so you want to sort of remove one of those. And in A level, most of the time, one of those functions is just a polynomial. So it's probably x squared or x, or it's like 5x squared, 5 square root of x, things like that. And so like, so for example, if it's in the case of like a x to the n f of x, and you know that this is an integral, then you just keep lowering that down until that polynomial disappears. So that's my best way of doing this. Right. Okay, I'm just going to quickly go through some of the other stuff that we've mentioned, and we'll talk through some of those. So, integration, we've done a little bit of it. Complex, I think we'll go through a bit with the moment stuff later. Stats. So stats is a bit tricky. There we have previously done a session on statistics, and you should be able to find them all on YouTube, I think. We've also done a session on integration, and I've also done a session on differentiation. I've also done a session on range and domain. So I'm going to go through those questions less. I will do more integration and differentiation because you guys ask for that kind of all the time. Um, but the other topics that I've just mentioned, do find them online. They are on YouTube, and I've gone through those for an hour. Mechanics, we'll go through that in a bit. Parametrics, um, parametrics most of the time leads to trigonometry. So just always remember if you've got a t equals something cos or t equals something sine, put that back into sine squared plus cos x squared. And then you'll be able to put those in together. Or if they're both equal to polynomials, like x to the n, x to the 5, you could probably rearrange and put them into each other. For proofs, um, there's actually not that many proofs that they can ask you about. So I would just recommend looking into the book because there's actually not that many. Um, and 3D vectors, think about them as normal vectors and then add and subtract. So Kristen has just asked a very good question of where can you find good resources for lots of practice questions? I've just found this, which I'm going to put into the chat. Oh, try and have a look at that. So this is Edexcel A-level maths exam questions by topic, which is a really nice way of looking at practice questions. And to answer actually your question of whether this was an exam question technique for an A star kind of thing, yes. So technically, to be honest, again, A star, you just need to know all the topics relatively well. Right? That's pretty much common sense. That's the difficulty with this. It's like the difficulty is not really know is not necessarily just knowing how to do a difficult question, but more of if I see a question, how can I recognize what type of question it is? And so one thing I mentioned beforehand is right from now until your exams, what do you need to do? This is general advice for most people, for everyone, right? Have a look at the topics themselves. Like go through this list and sort of tick which one do you struggle with? Which one are you happy with? And be honest with yourself, right? I probably can't do some of those questions in that topic, and just note that down. And then dip, figure out what level of uncertainty you're at. Do you have a baseline understanding? Do you have no clue what's going on with that topic? Or do you know most of the stuff? No, this is a list of all the topics. And then with that, go through the book. And the level of how much you go through that specific chapter, it depends on how comfortable you are with the topic. So if you know um, that you're not, but you know fairly well about this topic, but you don't know how to do some of the harder stuff, so look at the specific stuff at the end, or look at the mixed exercise. And so if you want to look at the free book, this page is absolutely goated. Um, this is one thing that actually, who was it? OJS put me on. So this has all the textbooks. You could look through year one, you could look through year two, and you just go through that specific topic and you just look it up. Yes, probably. And you do all the exercises in those books. Um, well, you don't have to do all the exercises in the books. Um, for a resource for OCR and your maths, like, you could probably look at Anna's archive and find them on there. Or you buy the book. You could also buy the book. You realize that 130 days is quite a lot of days. Um, and a lot of those days you don't really have classes anyways, for the last few bits. So just get to the point where you're doing past papers. And looking through a chapter will take you an hour, right? Yes, if you do other exam boards, you can definitely use Edexcel books. Um, just make sure it's up to you to check the specific specs. Didn't come up in my life. Well, depends on what you want to use. For M, you've asked about the vector content. Think about what you want out of the A level. Do you want to just get a good mark, or do you want to understand maths and for A level spec? The vectors content is pretty useful, and you'll probably come into it. So I would recommend looking through it, and it's all good. So someone's asked about speed. Speed is a very good point. Speed is, I think the way that from personally for me, the way I improved speed is by doing a good amount of questions such that I can immediately notice what topic it is. And if I know what topic it is, I know what sort of tools I have for that topic. And so I can kind of map how to do that question. And once you map it, then you can just do the rote stuff. And that's to solve your algebra. And if you can do the algebra with your calculator, or find some tricks to do with your calculator, then you can do that. And then once you're good at speed and you can comfortably finish with like 20, 25 minutes left to spare, then think about how can you check your working. And I would use my calculator to check my working. I'd use some of the different calculators. They might help you in that. Weird questions that never come before and they're quite hard. More questions. Um, I would listen. Yes. So from now until your exams, if you're comfortable with all the topics, but you're like, oh, I don't know how to do these hard questions that I don't come up with, go to the different past papers and just do them. I did get 5 A's last. And if you do if you do a past paper, go through it and highlight what questions you got wrong and put it at the front of the paper. Just write it down. And then you can look through all the past papers that you have done and can you spot yourself figuring out what are the most difficult types of questions that you just can't do. And if you'll feel like I'm getting some things wrong in integration, have a look at Matters Maths. There's some really hard questions. Matters Maths is definitely way above what you need for A level, but they're the sort of ideas of how to build those intuition. Yep, sounds good. We'll do 7 more minutes of exam questions, of sort of questions. How many papers do you think we should have done by our A levels? You can't, I mean, there's plenty out there. Oh, yes. There's plenty out there. Zaina, I think you mentioned about the My UCAT YouTube channel. If you can't find the other differentiation integration videos, I think they are on the Google Classroom, which I would just text OJS about. Yeah, so if you're making silly mistakes, just do a bunch of the past papers. If you finish all of Edexcel, go to AQA, go to OCR. You have a whole bank. Go to PMT, right, physics maths tutor, and then just do those other past papers because they're still the same types of questions and they're still the same, but they're actually asked in different ways, which is nice. Mm. Matters papers are a little bit too much. I don't think you should like you can do them. It will obviously help if you do them, but you don't have to. One stop if we haven't finished all the content as soon as possible. You'll continually, gradually build upon those things. So answer with precision. There are some tricks in your calculator. So if you are lucky enough to have a CG50, you can check your differentiation and integration, and you can get really quick at that. That's something that I like doing. There's some like vector stuff that is very helpful for further maths. I have a lot of sort of tips and tricks for further maths, which could be useful. Uh, how do you balance year 12 revision and year 13? Well, you kind of just have to with just do this past paper questions because you're still going to be using year 12 stuff, journal revision and homework and past papers. Okay. Um, if you feel like the homework is less helpful, I would probably do less. Yeah, CG50 is OP. I could probably like when I was doing like Oxford admissions, I did less homework and less revision and just did sort of like past papers. And I remember like at this point, at this period, I was just hitting past papers day in, day out. And I was just like, okay, I'm getting this question wrong. I'm getting this stuff wrong. Um, and just, yeah, going through those. What's really helpful is that in the book as well, um, there are the sort of like exam questions in the middle, like it's not like the review exercise, but yes, it is the review exercise. Those ones are great. Just go through those. Somebody just asked the great question of how do you achieve an A star? If you can comfortably, A-level maths, I'd say is probably one of the easier topics. I definitely found getting an A star in maths a lot easier than sort of chemistry or physics. So I would just say just do those past papers. The more past papers you do, the better. As usual, the more time you put in, the more you get out, right? Oh, also, yes, when did you finish the content? I actually finished the content before my class did. So I just read ahead in the book, and it takes you not that long. And use YouTube videos, right? Beat the classroom, beat the classmates. If you know that next lesson you're about to cover this specific chapter, do that chapter before them. What's stopping you? Um, how many hours did you revise? I have no clue. Year 12, when should I be doing past papers? I'm doing questions from PMT. If you're doing questions from PMT, that's very good. Um, if you do work at year 12, hit some AS papers. AS papers are helpful. Um, and then because they're at the right level where you're not running into too many year 13 topics. So that's actually a a great way to answer some of the questions previously, which is how can I revise year 12 topics and also year 13 topics, but have a divide? Use AS papers because they will test year 12 content, right? And so then you can kind of just like go through that and realize what did I fundamentally get wrong in that exam question in that exam, and then you can look at the specific year 12 topics that goes through. We will be doing some questions in a couple minutes. Do, do, do. There's a lot to do, but enough time. Yeah, is it worth spending my time making a list of all techniques? Yes. Otis has said, yeah, exactly. Get ahead with the year 13 content, finish as soon as possible, and then you get the extra month to just do past papers. Cheat sheets, no. Where's your best do you approach easier questions first or harder ones first? Oh, yeah. If you are struggling with time, I do this thing. which if I'm doing a like a pass, if I'm doing a paper, you know how you have the questions, right? I would actually look at the specific time that I started. So if I started at 12:00, I would write 12:00 next to the exam question. And then once I finished the exam question, I would write the time I finished that question. So like maybe like 12:05. So I know that in that one question, it took me 5 minutes. And so you can keep doing this for question two and question three. And it could be like 12:12 and 12:14. And you can have a good sense for yourself about how quickly you're doing each question. And if you know that in a specific paper, there's 15 questions, you're given an hour, you should be aiming for 4 minutes per question. You can sort of work out by per question how fast you want to do it. I worked this out when I was in uni, and that has helped me quite a lot. Yeah, cheat sheets for PMT is very useful. I would recommend making your own, but just make like a little skeleton. This is my topic. These are the key things I should care about. These are the things that I really find difficult. And then target those. Cool. All right, 9:30 is hit. Let's do some exam questions. Let's do some integration. And there are some particularly difficult ones, maybe. Um, Oh, okay. So you might be hit something like this. Um, if you want a rundown of integration, please look at yeah, if you want to run down of integration, please look at the YouTube video that we've created or that I ran with a previous session on differentiation and integration. Okay, so let's have a look at this trig identity question. I haven't seen this question yet, so if I was looking at this, what would I be doing? Okay, so I've got sine 2 theta over 1 plus cos theta. The integral from d theta equals 2 minus 2 ln 2. So, my first instinct is I see sine 2 theta. I'm probably going to be using a sine double angle. So I just write down sine 2 theta is equal to, I know that's going to be 2 sine theta, 2 cos theta. Okay. Um, and I have like 1 plus cos theta. Because I see that 2 ln 2, I'm thinking there's probably going to be this natural log generally means that you have something where it's 1 over a function, again, a 1 over f of x, right? Oh, uh, stop the share. Share again. Can you guys see the whiteboard? Yep. But, and so you're thinking, okay, so I'm probably integrating pi over 2 over 0, 2 sine theta cos theta over 1 plus cos theta. And I see this natural log, which might mean that I'm integrating the lower function. And so I would, in this case, probably just use a U substitution because in my head, I'm thinking this is probably the outcome of differentiating 1 over 1 plus cos theta. And I multiply by the derivative of this, right, which is a sine, which is why this comes in. And then this cos theta probably comes out because of a U substitution. Now that was a little bit quick, um, but does that make sense? It's kind of like my thought process there, right? You look at this, I see a natural log. You're, I look at this, right? I see a natural log and I see a fraction. You're probably going to be differentiating something that looks like this because when you integrate 1 over a function and it's the something that looks like this, then this is the integral of 1 over f of x. Yes, you have to reverse engineer the question. So this is the sort of like exam technique thing of this question, which I wanted to cover. I am writing on a Miro board. Uh, no. Well, kind. Yes. F of x over f dash of x, right? Something like that. And so, yeah, it's sort of like this reverse chain rule. So let me just continue this. And so from this, I would just go for a u substitution. Maybe u equals 1 plus cos theta. That's helpful, right? I don't want to have something that's 1 over 1 plus u because that's not as nice to integrate. So I'm just going to do that. Then I take the derivative of this. Du over d theta is equal to negative sine theta. And I would just plug this in. So this is in with respect to d theta. D theta equals minus 1 over sine theta du. Plug this back in, and I get something like 2 sine theta cos theta over u, right? 1 plus cos theta, multiplied by 1 over negative sine theta du. I will amend my limits later, right? And then I see that I can take out the minus 2. I can remove this sine theta, and then I get something that looks like minus the integral of cos theta over u du. And this is nice because I can see that if I know that u equals 1 plus cos theta is just u minus 1. So I get this, and it turns out it becomes minus 2 integral of u minus 1 over u du, which is minus 2 integral of 1 minus 1 over u du. Obviously, work out what your limits are here by plugging into this equation, and you can do this. And this validates what we thought previously, which is that you're probably integrating 1 over x because you're getting a natural log. And so that's why you would use a substitution for 1 over. Okay, that's trig. That's a difficult trig identity question. So have a look at that. Okay, someone mentioned parametric integration. So here is one. Which book has geometry? Don't know what book has geometry. Yeah. If make it to one letter, so then it's easy. I don't know which book has geometry, I'm afraid. So sketch of the curve with parametric equation. X equals natural log t plus 2. Y equals t plus 1. State the domain of value. Oh, look, we're doing a domain question, right? Domain of values of x for the curve C. Domain is what I put in. So what values can I put in here? If t is greater than minus 2/3, um, then I can sort of see what my values of these are. I probably even just go into drawing what x is, right? X. I'm looking at a natural log, which I know looks like this, and it's t plus 2, so I've shifted it minus 2 to the left. So it looks sort of look like this, right? And I'm looking for t is greater than minus 2/3. You're probably looking at here. So I've just used my calculator to work out what is the natural log of minus 2/3 plus 2. And that's going to be my smallest x value. Makes sense, right? And that smallest x value is probably in negative x. Um, and that's probably it. That's my domain of values, I think. Yeah. So it would be x, so minus 2/3 plus 4, so minus 2 plus 6 over 3. So because natural log of 4/3, so its x is greater than natural log of 4/3. And I see that because I've drawn the curve, and I see that this natural log goes way down here and way up here. So if all my t values are only from this onwards, I can see that all the x values I get is just from natural log of 4/3 over. Right. And so that's my domain of values. That was easy. The finite region R shown in keep it in natural log form. For because okay, so for Furkan, it's just draw this, plug in minus 2/3. You see that everything is above here. Okay. B. Use calculus to show that the area of R is natural log of 3 over 2. So the finite region shown here is this. So for parametric integration, or let's just write, we want to write the function of x with respect to x, right? And so general graph shapes. So natural logs, exponentials, polynomials, trigonometry. That's it. Finite origin R. I think there's a, yeah. So you know that what you're trying to do is the integral of y dx, right? You can look at this and see that this is similar to doing y um, dx over dt, y dx over dt. Now I know that you shouldn't be thinking about this as fractions, but you can see that they kind of cancel out the dt's. And so from here, you just go straight into here. So because then you're converting, mathematically, you're basically converting dx into dt, but you're converting the domain from x to t. This is actually just a u substitution. That's what you're doing with parametric equations. You are saying that x equals natural log of t plus 2. Therefore, dx over dt is equal to 1 over t plus 2, right? And then you can rearrange for this so that dx is equal to 1 over t plus 2 dt. So you plug that back in, I get the integral of y, throw that in, that's 1 over t plus 2 dt. And this is equal to this dx over dt. All right, that's what you're doing. You know how to do U substitution. That is what trig identity is doing. And then you know what y is, which is y equals 1 plus t plus 1. So this becomes the integral of 1 over t plus 1, 1 over t plus 2 dt. You are integrating two functions, two fractions multiplied together. So this should automatically scream, what's it called? The one where it's like a over. No, not product rule, because product rule is differentiation. This is um, partial fractions. Thank you very much. It's when you convert this into a over t plus 1 plus b over t plus 2 integral dt. Work that out with partial fractions. And from here, it's pretty simple because you see that t plus 1 differentiates to nothing, right? And t plus 2 differentiates to nothing. So this is just the natural log of t plus 1 plus the natural log of t plus 2. And then you'd consider your limits. And you probably have these, like, these constants that you can determine yourself. To work out your limits, look at these, right? You're integrating between natural log of 2 to natural log of 4. And so then you would convert this into t. Because you know x equals ln t plus 2, plug this into here. So that's natural log of 4 equals natural log of t plus 2. So you know the integral is from t equals 0 to t equals 2. Yeah, you would simplify using log rule. Okay, that's integration. I'm going to go through some difficult differentiation now, and then we'll go through some other questions. All right. Let's see if there's anything particularly difficult. That's trigonometric differentiation. Oh, that looks hard. A is not supposed to be on both, you're right. It should be A and B, but obviously it's not really A and B either. So they're just constants that you should work out yourself. Okay, question 15. Here is a sketch of the curve with equation this. I get something that looks like 4 sine 2x over e to the square root of 2x minus 1. Well, goodness me, that looks terrifying, right? Let's take it step by step. The curve has a maximum turning point at P. What does that tell you? You know that the derivative here, dy over dx, is going to equal 0 here, and at Q is also a minimum turning point. Dy over dx is going to be 0, 0. The difference between these two is that the second derivative at the top is going to be negative for the top, and the second derivative at the bottom is going to be positive, right? So that should help you a little bit. Show that the x coordinate. So this is also helping you with speed. As you read it, note things down that you know about the question. Show that the x coordinates of point P and Q are solutions of the equation. This is, as somebody mentioned, is going to be quotient rule. Because as you can see, I have a whole function here, which is just sine x plus these constants, which you don't really care too much about. And this is, again, also just um, a function in this. So that is just e to the power of root 2 x minus 1, which is actually just e to the power of root 2 x over e. And this is just a constant. So you don't have to care about this too. This is actually just integrating e to the kx, which you should be comfortable with too. Um, so as you can see, you've got two functions that are actually quite easy to integrate, or easy to differentiate quite nicely, because this will go down to k e to the kx, and we have sine kx here, which goes down to cos k cos kx. So that's where the quotient rule will come in. And then using your answer to part A, find the x-coordinate of the minimum turning point with equation this and this. This is just sort of your movements. If f of 2x, you are shrinking everything down. So your x-coordinate's half. And for this one, 3 minus 2 f of x, think about doing it step by step. So multiply it by minus 2 and then add 3. Right, think about, and this is only just a vertical stretches. So you're flipping it around, stretching it by minus 2, and then you add 3. Okay. Yeah, for exam, quite, I mean, every time I do exam papers, I do them in order. So, uh, CG50 gives you the answer for B? No. Oh, for the tan, that should come out from integration, from differentiation. You should get something that looks like something like, oh, you know, let's do this quickly. The derivative of 4 sine 2x over e to the root 2x over e is going to be, I use low d high minus high d low over the square of what's below. So I take the low, e to the root 2x minus 1. Derivative of the high, that's going to be 4, I know you'll multiply by the 2, so that's going to be 8 cos 2x minus high, so that's going to be 4 sine 2x. The derivative of the low, so that's going to be root 2 or e to the root 2x minus 1 over the square of what's below. And I would just put that as e to the root 2x minus 1 squared. And I know that at the point P and Q, this is when the derivative is equal to 0. So if you set these apart, set these equal to each other, the only part you care about is just the numerator. So how you get the tan is you can see there's a cos here, there's a sine here. If you let it equal to 0, you get something that's like cos x equals sine x and some exponentials here and there. And so what you get is that you can rearrange this for tan x, you could divide by the cos to make some full function. And turns out that functions end up being to be root 2. Okay. Wow. So we've done differentiation, we've done integration. Any other specific topics? Proofs. Sure, we can have a look at some of the proof stuff. Where are proofs? Oh, I mean, we just did a domain question. So the topics I found hardest, probably differentiation, integration, same as you guys. Oh no, I actually found proofs quite difficult, but then I realized that they're not as hard as I thought I thought. Because for proofs, they're usually the same thing. Oh, proofs are just in year one, I think. Where are proofs? Okay, I can't find which specific. Year two, proof by contradiction. Oh, yes, in algebraic methods. Yeah, 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 yeah. Okay, sure. Let me have a quick look at that. Okay, so for proof by contradiction, there's only really a few things, and they're the examples in the book. Right? So such as no greatest odd integer. add by 2 and you get another odd integer. Proof by condition that n squared is even, then n must be even. So for this, most of the time, think about if I was odd and if I was even. And if I was odd, I'm thinking it's n 2n plus 1. If I'm even, I'm thinking about 2n. And n is a integer. N is any integer, right? So then you can just think, okay, so if n squared is even, um, or okay, so for contradiction, it's just the step. You have your assumption, and then you can prove that wrong. So let's prove this one. Prove by condition that n squared is even. Then if n squared is even, then n must be even. Must be even. So assume. So what you want to do is assume that there exists a number n such that n squared is even, but n is odd, right? And so if n is odd, let's write n equals to 2k plus 1 because we know it's odd. And from there, you do n squared. That's 2k plus 1 squared, which becomes 4k squared plus 4k plus 1, right? And so you can see that this is a multiple of 2. You can pull out the 2k squared plus 2k plus 1, which means that this must be odd, and therefore it contradicts. That's how you do proof. Yes, you can send me a question to go through. Root 2 is an irrational number. That's always really common, right? Oh, so level of maths questions, I don't know. Um, but you should be able to work out whether you find them really difficult or not. Don't do anything that's too tacky. The p-value when using hypothesis testing, whether it is, I'm pretty sure it's just whether it's um, two-tailed or one-tailed. If it's two-tailed, half the p-value. If it's one-tailed, you just use the p-value. And your p-value should be in the question. It's like 0.05. Can we change them so I can end them there? Oh, no. Can you just tell me what question it is? From which paper? Okay. Let's do, let me just go back to the questions that you guys have mentioned. Trig identities like arrangements, moments, mechanics. Yeah, I think I'll go through some mechanics. I'll do some moments questions and I'll do a projectiles question if that's all right. Also with that, I don't know what paper you're asking for. Okay, so moments. Oh, let's do this. Right. So a plank AB of mass M and 2A rests with its end A against its rough vertical wall. The plank is held in horizontal position by a rope. So if I was to do this in the question, I see this question, how would I think about this? AB, mass length of M, length of 2A. Makes sense. Rests with its end A against the rough vertical wall. So there's friction here, right? Um, the plank is held in a horizontal position by a rope. One end of the rope is attached to the plank at B, and the other is attached to the wall at C, which is vertically above A. Makes sense. A small block of mass 3m, so I'm going to put 3m there, is placed on the plank at point P, where AP is x, right? And the plank is in equilibrium in a vertical plane, which is perpendicular to the wall. Great. The angle between the rope and the plank is alpha, where tan alpha is equal to 3/4. Nice. The plank is modeled as a uniform rod. Okay, that's key. Uniform rod means that our mass M is in the middle. There's mg here, right? That's what I would write. And the block is modeled as a particle, and the rope is modeled as a light, inextensible string. Great. So I know that the block here is going to be also 3mg, right? Because the force is mass times gravity. Using the model, show that the tension in the rope is this. So I know that with here, there must be two tensions. A tension that goes to here and a tension that's here, but you don't really need to care about this one. So not really that relevant. And then you would just do moments on the bar. So if in this case, I would actually just look at the point here and I look to the right and I add the ones that go down as negative and the one that go up as positive. So if I go down and I look, and I'm following, if you just follow my pen, I think, okay, nothing here, nothing here, nothing here. Oh, here we go. I've got negative MGA because I'm A length in halfway of 2A and it's going down as negative. Then I'm at 3mg. In this case, 3mg here is also a negative because it's going clockwise. So that's going to be minus 3mg, and the length is x, right? And then I'm going to plus, because it's going upwards and it's going anti-clockwise, of t. Um, and that t here, I need to think about the proportion of this that is vertically up, right? So that's going to be t sine alpha. So that's going to be plus t sine alpha multiplied with the total length from the pivot point, which is 2a. Because I'm told that tan alpha is 3/4, I can immediately work out what sine alpha is. And I can do that also by knowing that if this is alpha and it's a 3/4, that's going to be a 3/4/5 triangle. So I know that sine alpha is going to be opposite over hypotenuse, which is 3/5. You plug that in, and I get minus mga minus 3mgx plus 3/5, so that's going to be 6/5 a of t. I know this is equal to 0 because the total anti-clockwise and clockwise moments equals 0, right? Because this is in equilibrium and it sits still, which means that the total negative should equal total positive, which means this is going to all equal to 0 because I'm putting all the negatives of the clockwise and the positives anti-clockwise. And so from this, you should rearrange this pretty easily to be that 6 over 5at equals 3mgx plus mga. Um, and you can see that t equals 5 over 6 of, what's that? mg, 3x plus a over a. There you go, you get that top part. The magnitude of the horizontal component of the force exerted on the plank at A is 2mg. So let's write that down. T sine alpha is because if this is T, this is broken down. If this is T, then this is the angle alpha. Then this is T sine alpha, and this is T cos alpha. Like that. It's general trig, right? Right. Magnitude of the horizontal component at A, horizontal, is 2mg. Yes, indeed. 2mg. Find x in terms of a. And at this point, you would want to be thinking about again, this rod as well. And you just think about this rod and think about what the forces are on the rod. You've considered all the vertical forces. So now you should consider all the horizontal forces. And you could again do the same thing and look it to the right as my positive direction. So I see that there's a plus 2mg here going to the right. But then on the opposite side, I've got a backwards force that's from the t. And that actually comes from this t cos alpha that I mentioned above here. So this becomes minus t cos alpha. And that's it. The rest of the stuff won't have a component because they're all vertical forces. And so if this is equal to 0, you should be able to see that t cos alpha equals 2mg. And you know that from here, cos alpha is going to be opposite over hypotenuse, like SOHCAHTOA, so adjacent over hypotenuse. So cos that should be 4/5, right? And so here we get 4/5 t equals 2mg. Um, and so t equals 10 over 4mg. And you just use this equation with this equation, plug that in, and you should be able to rearrange for x to equal in terms of a. The force exerted on the plank at A by the wall acts in a direction which makes an angle beta with the horizontal. At A, you want to think about the horizontal component of the force. at A by the wall. No, no, the force is on the plank at A, acts in a direction which makes an angle B beta. Find the value of tan beta. Okay. So in this case, you want to think about the total forces on. So when it comes to mechanics questions, when it comes to these statics questions, there is three things, right? There's horizontal force, vertical force, and the total moments. So we've done the moments, we've done the horizontal force. You can now consider the vertical force. So the vertical force in this case is just going to be if I've got mg coming down and 3 mg coming down, I should have 4 mg here. Or it actually becomes like I think it's 4 mg minus t sine alpha. Right, you can see that now everything is balanced together. And then from this, you've got a little bit of a triangle here. You've got 2 mg here, then 4 mg minus t sine alpha. And this would be your angle, beta. Would that be the friction force going up? Yes, correct. That's the friction force that holds it up. And then the rope will break if the tension in it exceeds 5 mg. Explain how this will restrict the possible positions of P. Um, I mean, it just means that you can't go further apart. You would probably work out what the limiting value of x is here. Okay, and that's all that I have time for, but I will go through a couple of things. I think there are some points that some people have mentioned, and I'll be sticking around for about 5 or 10 minutes. I don't know if I have the link to the Google Classroom. I would ask Jess about that. Let me go through what feature. June 2019, paper 2, Edexcel, question 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay. Okay, so there is no Google Classroom, I'm afraid. You guys have to use the YouTube link that he has put previously in the chat. Okay, so for this is the question 8, right? Find the value of this. This is just series. So here it's infinite, so it's an infinite series, infinite geometric series, right? Oh, let me just do a recap of series. There's only two types. There's arithmetic and there's geometric. Geometric. Arithmetic, you've got one that goes to, and you can work out that goes to n, and geometric, there's one that goes to n and infinity. So arithmetic as n is going to be n over 2, uh, 2a plus n minus 1d, which is the common difference. Whereas geometric, that's going to be your um, r to the power of what's like 1 plus r to the n, I think. A 1 plus r to the n over 1 plus r. So that's something like that. It's in your formula booklet, so you should know that one. But the one that you want to remember is S infinity, which is a over 1 to the power of n. Yes, 1 plus r. A over 1 plus r. Yeah, that's it. And then, so with this one, this is just, you can, 1 minus, yeah, exactly. It is 1 minus r. Thank you. Because I knew there was a sum restriction on it. 1 minus r to the n. Yep. Good. And so with this one, you can actually take out the 20, which can help you. 20 infinity of this, r equals 4 of a half to the power of r. Going from 4 to infinity, well, you can kind of just start with, you want to start with the first value. So you want to work out what a is, and you want to work out the common difference, or the ratio, and the ratio would be half. So a is going to be when r equals 4, right? And so in this case, this is just going to be 20 of at a half to the power of 4, which is going to be 1 over 2, 4, 8, 16. So 20 over 16, which is going to be 5/4. Right. And that's my A. So in this question, it's 5 over 4 divided by a half. And that becomes 5 over 2. So that's your final. The modules of R mean here. So you're right. It's kind of a bit, you're kind of like messing around a little bit. But when we look at our general cases, R means the common ratio. here, right? And D here is the common difference. And so here with a common ratio, this is a different R than the common ratio. In this case, your common ratio is actually R is equal to a half, and this R should really be written as like a K, just to not mix things up. But they've kind of like purposefully done that because each time you're multiplying by a half, so that's your common ratio. And so then with this, you want to go from I to 2. This one's a bit tougher, but I would assume you are using your log stuff. So this is going to be log of n plus 2 minus log of n plus 1. And you're going to be going up in steps or that's an interesting one. I would have to think about that. Maybe at the moment, I would look at think about writing n plus 1 and n plus 2 in a different format. So I put n plus 1 over n plus 1. So that's going to be 1 plus 1 over n plus 1. Or that might be something that you could do. Um, but that doesn't feel right. I think this is your best bet going from one takeaway. Oh, I see. This is difference. This is the difference way. So it's actually, I think this is a form, this is a bit more of, no, it's n equals 1, right? You split this up to be log of n plus 2 minus log of n plus 1, right? And you'll realize that if you actually write this down, you have log of, I have n equals, from it's n equals 1 to n equals 41, right? So I could put n equals 1 here, n equals 2, n equals 3, and so on. You'll realize that you get log of n plus, so for n equals 1, let me just log of n plus 1 minus log of n plus 2, right? Yeah. Log plus n plus 2 minus log of n plus 1, right? For n plus 1, this is log of 3 minus log of 2. Then the next one is log of 4 minus log of 3. And then log of 5 minus log of 4. You'll realize that they cancel out. So you can see that this one, log 3 cancels out with this because you're adding all of these up. Log 3 minus log 3, log 4 minus log 4, log 5 minus log 5, and so on until you get to the last value, which is n equals 48. And you get log of 50 minus log of 49. And if you follow that through, you'd cancel out the log 49 from the previous top one. And so you end up getting log 5 of 50 minus log 2, log 5 of 2. And then this is log 5 of 5 times 10. Or, no, sorry, 5 squared times 2. So you can see this as log 5 of 5 plus log 5 of 2 minus log 5 of 2. These cancel out, and this becomes log 5 of 5 squared, which is just 2. So your answer is 2. There you go. That's how you do that question. Hopefully that was fun. That was actually interesting. 3 marks is kind of insane for that. Yeah, you're right. But this is a further maths thing. Okay. Any final questions for this session that you guys have? I'm happy to stay for a couple more minutes. Hopefully you guys had what do you guys think of this session? Hopefully this was useful. But yeah, let me know if any feedback. Log base 5, those are, that's because that comes from the question. You see that? Log base 5. Well, you just saw what I did there, right? I didn't understand how to do that question. And I kind of just thought about it. And it's tough. But with this question, I would think about just plugging it in, trying. Like I was like, okay, is it this? No, right? And then I just plug in 1, 2, 3, 4, 5, 6, 48, and you get this. Yeah, that's that. So yeah, this is very much kind of like trial things out, and you might get it. But at the end of the day, this is 3 marks, right? So try to pick up marks which you're strong at, and try to pick up marks that you are used that you can comfortably get. Just to double check, just to go through what we've done. We did moments there. We did a hard integration question and a hard differentiation question there, and then we sort of went through some of the topics there, and then some general sort of exam help stuff. I'll be here for another 2 minutes or so. If there's any further questions, let me know, and we'll be running a so you mentioned content around 2 months. Yeah, pretty much. Website and the book from the beginning of the session. Sure. Oh yes. What would you like? What would you guys like to do in the next session? So yeah, I'm happy to do a paper run through. That'd be really fun. So that's for the books. And then yeah, I can do 2025 paper one, paper two, paper three. Uh, when do you start? As soon as possible. I'd start past papers now, but make sure you know what topics you're good at. Sure, I can do that. Just do try to estimate 1 mark per question. I think that's probably the best rule of thumb to use. Uh, this is the topic. These are the questions for some stuff on all of kinematics, including project. I don't think I can do a full hour on just one topic, but we can do some more questions on project. I could do a projectiles question later. How should I learn the content ahead of class? Books. That book, whatever exam board it is, you should have a textbook. Look into that chapter and read it. It will take you an hour and a half, maybe an hour to just sort of like read it. It takes you 20 minutes to read it and an hour to understand it. Um, and it will save you so much more time in ahead of class. And if you have questions, ask them in class. And that has saved me a lot of time. YouTube is for maths. Ooh, I didn't actually use that much of YouTube. I kind of use the books because I'm a big fan of like practice-based learning. Okay. Um, I think if that's all, I'm happy to end the session there. Just stop sharing. Right. Thank you very much. I will be heading back to the UK today. This is then I'm just gonna end. Oh, just I think you can end it. I assume you can end it. Yeah, this is I'm in Massachusetts. I don't know if you guys can see this, but there's snow. There's a lot of snow. I don't know if you can. No, I don't think you can. Oh, there you go. There's a lot of snow out here. We're in very cold, sort of Williamstown, Massachusetts. Pretty sick. All right. Have a good day, guys. See ya. No, I'm only here for a couple of weeks. I'm coming back to Oxford and I'll start lessons again tomorrow.